Thanks for organizing and for the invitation to speak to you all today. And so the title of my talk says I'm going to be focusing on the mechanisms responsible for the recent trends in Antarctic sea ice, the extremes in both expansion and decline. Coincidentally, Ethan did a really great job of seeding some of the ideas I was going to talk about in this talk, as well as Marika and Francois from yesterday. So I want to quickly acknowledge two people, Lexi Arlen and Chloe Cheng, who are students in my group, who helped me with some of the analysis and also just bouncing ideas off them about different things. So, sort of set the stage here. You've seen this plot yesterday. This is showing the trends, monthly average trends in Antarctic sea ice anomaly. Going back to the satellite records from NSIDC climate data record. And what you can see is that in recent years, since around 2016, there's been this prolonged period of sea ice decline across the Southern Ocean. And prior to that, there was this period of sea ice expansion, right? And what's really remarkable is that you have basically this record high in sea ice extent, almost immediately followed by this, what was then the record low, and that happened within roughly less than 5 years, right? And so when I say whiplash, I'm referring to this extreme swing in Antarctic sea ice extent. And so a number of studies, in particular Ariana and Ed Doddridge, they did some statistical analysis to show that there's actually been this very clear change in the behavior of Antarctic sea ice. And you can sort of delineate like this first period of the satellite record where you have relatively weak trends, low internal variability, to this more recent period where you have enhanced variability, and of course you have the expansion period and this decline period. And so for most of this talk, I'll focus on this 2005 till present. I'll be using Argo data, and this overlaps with our in situ Argo data availability. And so looking at the spatial extent of these anomalies, here I'm showing the anomalies in sea ice season length. And so for each grid cell, how many days did the sea ice occupy that grid cell? And these are deviations away from the average. And so, so here, sort of group them into the ice expansion period from 2007 to 2015, and the ice retreat period following after. And what you can see is, in both cases, relatively circumpolar patterns, especially in the White Sea, for both the expansion and the retreat period. The order of magnitude here is around 20 to 30 days across these subpolar gyres. And so if you think about, your ocean heat uptake, that's a big deal, right? And I wouldn't say, they're almost mirror images of each other, but you do see some differences in the Ross Sea here, right? And I want to make a point here to highlight that much of the changes we're seeing in the circumpolar average is being driven by changes in the White Sea. And so if I were to make a plot of the sea ice area anomalies for the White Sea and compare it to the circumpolar anomalies I showed earlier, you see a pretty tight correlation, especially for the last 20 years, right? And so to help us zoom in and focus on where we need to, the region we need to understand, it's clear that it's imperative that we need to understand the White Sea in particular if we want to understand these recent changes. Okay, so there's been a lot of studies, trying to explain these changes, both for the expansion period and the subsequent retreat period. This is not an exhaustive review of all these studies, but I just want to highlight some of the recurring themes. So for the pre-2016 sea ice expansion period, a lot of studies have focused on the role of the strengthening of the circumpolar westerlies, which would enhance northward Ekman transport and promote ice expansion into the circumpolar channel. Other studies have focused on the impact of surface freshening, which increases stratification and sequesters heat at depth, and therefore promotes cooler surface temperatures and more ice growth. And then at least one study has focused on the role of the Monroe's Weddell-Sea convection and the role it can play in driving variability on interannual and decadal timescales. And so for the post-2016 sea ice decline, we see a similar set of studies highlighting the role of the circumpolar westerlies, but this time specifically the impact of enhanced upwelling. And so as you shift that circumpolar westerly jet poleward, you tend to increase the negative wind stress curl, or you make it more negative, which enhances upwelling of circumpolar deep water. Studies have also highlighted the role of enhanced poleward advection of warm air, especially for the 2016 sharp decline in sea ice extent, and also for different minimum sea ice years like 2023, for example. And then the other studies have highlighted ice albedo feedbacks, i.e., after some perturbation to the sea ice field, the ice albedo feedback will tend to sustain those anomalies going forward. And so what I want to highlight is these two sets of mechanisms. And the reason being is because they have an underlying sort of physical driver. And the underlying physical driver is the sort of the trends in the southern alluvial mode, which describes the intensification and poleward shift of the circumpolar westerlies. And this bottom plot here is showing the trend in the SAM index. So positive means more poleward, intensified circumpolar westerlies, and we see this very apparent trend towards the positive phase since 1980, right? And so the consequences of that are as follows. And so in sort of one sort of simple theory, we might expect that with strengthening of the winds, as I mentioned, you have an increase in northward eggman transport, which happens relatively quickly. That promotes surface cooling in the circumpolar channel and sea ice expansion. And then subsequently, in the following years, you have a spin-up of the operation decancel and enhanced upwelling in the sea ice region. And so what you'd expect is while you have this expansion in area, you have this slow sort of accumulation and upwelling of warm water, which would slow sea ice growth. And eventually, over time, this upwelling, this slow response would overwhelm the expansion and lead to net sea ice loss in the long term. At least that's one possibility. And so one of the first study to sort of propose this was Ferreira et al. In 2015, and they did an experiment using an aquaplanet configuration using the MIT GCM, and you see this very clear cooling followed by long-term warming. They did a similar study experiment using CCSM, and they found similar pattern, but where the warming occurred over a shorter time scale. And so this is all nice, but in subsequent studies, people have tried to repeat this using different models, and you get this very famous spaghetti plot of responses from these different models, and I think this is seen at 6. And so this is looking at the sort of temperature anomaly following a 1 standard deviation increase in the SAM index. And so models generally capture this initial cooling, but roughly half of them remain cool in the surface, and another half warm in the long term, right? And you have some that do some interesting things here, right? And and if you look at the sea ice extent, this is a study from plot from Marika's paper from 2017. You see a similar thing. So generally speaking, these different lines are different models, and following a 1 standard deviation increase in SAM, you tend to have sea ice expansion. Many of these models just retain that expanded state. Some very quickly shift to sea ice retreat, right? And so there's a lot of so this 2 timescale hypothesis for the response of the upper ocean and sea ice to circumpolar westerly wind changes is I think is still sort of debated in the ocean world, and I have a lot of thoughts about it. But I think it's a useful starting point for thinking about what's happening in recent years. So what one might expect then is well, the reason this is also helpful is because it's the only mechanism I know of that you can potentially link the CS expansion with the CS retreat. And so that's what's a useful starting point. So thinking about the CS retreat phase, one might expect, based on this theory, that it's due to enhanced upwelling. And so some studies that have been already highlighted here have suggested that it was in fact what happened. So Meal et al. And also Pritch et al. They showed this time series of upper ocean temperatures, and preceding the 2016 sea ice decline, there was this apparent buildup of heat at depth, right? And you see the same thing down here. The problem with that is, one, it relies on this gridded agroclimatology that only goes to 65 south, and so we're missing much of the sea ice zone. So it's missing everything south of this red line. And in addition to that, we still don't have a good sense for the spatial structure of these anomalies. So what we wanted to do was to sort of build on that and sort of look at the data that's actually poleward of the ice edge, and so in a sense, just like build our own climatology using argofloats. And poleward within the sea ice region, poleward of 65 south, there's almost an order of magnitude decrease in argofloats, but there's quite a lot. And I think at this point, we actually have enough to start looking at interannual variability over the last 20 or so years. And so this is the plot just showing profile counts over these 5 to 7 year spans in a 2x4 flat one box. And pre-2007, there's not a whole lot of argofloats, barely enough to sort of look at make an annual mean. But since then, and especially for the CS expansion and CS retreat period, we have fairly decent density on sort of annual timescales, especially in the Weddell Sea, where is the region that we care about the most. As a former member of the Steve Reiser lab at UW, I'm obligated to point out that this is not how you deploy an argofloat. You need to gently lower the float into the water and not chuck it over the side of the boat. Right? So, now you know. All right. So what we're going to do with the float data is relatively simple. So this is an example temperature salinity profile from the Weddell Sea. I don't remember exactly where this is like data from a single float. And what we're going to do is track the magnitude and depth of the subsurface temperature maximum. And this allows us to track this warm deep water layer, which is a modification of circumpolar deep water. We compute a number of other metrics like mixed layer depth, mixed layer salinity, temperature, the gradients in the thermocline, halocline, but for this talk, I'm just going to focus on the simple metric of Tmax and the depth at Tmax. And so what we're going to do is just plot that over the entire circumpolar region. And so this is what this looks like just if you average all the data. So on the left is the subsurface temperature maximum. On the right is the depth of that maximum. And so you can see that in the Weddell, it's relatively cold. And you can see this is the cyclonic jet of the Weddell Sea, and there's inflow of circumpolar deep water, which becomes modified, which becomes warm deep water. And you see that this temperature maximum is relatively shallow in the subpolar gyres, in the Weddell gyre and the Ross gyre over here. Okay? And so what I'm going to do next is show you these same data, but I'm going to average over the CS expansion period and the CS retreat period and show you the difference. Right? And so when you take that difference, on the left, you can see this is the delta in the Tmax. So taking the difference between the ice retreat and ice expansion period. and this is showing the delta in the depth of that Tmax. And so what you can see very clearly is that in the wet LC, the subsurface has very clearly warmed, and there's a spatially coherent pattern. You also see that the subsurface temperature maximum has also shoaled quite a bit, right? And on the order of 60 plus meters in some regions, right? And so as someone who's looked at these flows for a lot, this was quite shocking. I've really used to looking at these annual means and just didn't appreciate how much they can vary interannually. And so this warming and shoaling pattern, is very, very apparent in the wet LC, also apparent along the margins of East Antarctica. And in the Ross Sea, we don't really see the same signal. There's a lot less data there. And if anything, it's showing the opposite, right? And so, so this first result sort of confirms what these earlier studies, told us using the Argo floats mainly in the circumpolar channel. But now we can see that this upwelling signal is mainly confined to the Weddell and the East Antarctic region, right? And so whatever is driving the sea ice loss in the Ross is probably not due to ocean upwelling. Okay, so all that's setting seems good. We can sort of wash our hands and say, okay, that confirms it. But there's some complications. So what I'm doing here is sort of disaggregating that large temporal average. And so what I'm showing here, this is the change in subsurface temperature maximum for different 5-year periods relative to the period before it, right? And so this 2011 to 2015 is showing the change in temperature maximum relative to the previous 5 years, and so forth. And so what you see is that this warming and shoaling of the thermocline started well before the sea ice started to retreat, right? And so in particular, it warmed and shoaled the most during the sea ice expansion. And so if we're going to argue that it's the upwelling that's driving the sea ice loss, then you need to explain why it didn't drive sea ice loss when there was a sea ice maximum. And so that continued through 2016 to 2020, a little bit less so. And then in more recent years, the thermocline trends have sort of reversed a little bit, right? And so if you zoom into the wet LC and look at the temporal variability, and so this is now showing a time series of the depth of the subsurface temperature maximum, or this is the depth, and on the right is the actual Tmax. And highlighting here just the ice expansion, ice retreat period. I'm going to mainly focus on the depth of the subsurface temperature maximum because the change in Tmax is relatively small, right? But nonetheless important. And so just to sort of drive home this point, and so during this ice expansion period, you have rapid thermocline shoaling, and this record maximum sea ice extent occurred when the thermocline was relatively shallow, right? And if you compare that to this record minimum in sea ice extent, it was actually more shallow and similar temperatures for those two times, right? And so something else is going on, right? And I want to quickly point out here that these trends in Tmax are somewhat consistent with wind stress curl trends, and so I say somewhat because there's this during 2015 there was this strong upwelling anomaly, deep negative wind stress curl of the Weddell Gyre, and that's consistent with this rapid increase in the thermocline depth. But if you look at the 2010 to 2014 period, you had this apparent shoaling in the Tmax, but the wind stress curl was sort of doing something different, right? So so the big question here is why did sea ice expand during this rapid shoaling, and or to put it differently, what was suppressing this upwelling of warm water? And Ethan nicely sort of set the stage for this. And so I think a big part of what's missing from the story here is the freshwater fluxes. And so on the left, I'm showing for the wet LC, mixed layer salinity over the 3 periods. On the right, I'm showing the subsurface mixed layer salinity gradient. And so what you can see is that for the ice expansion period, summertime mixed layer salinity was a lot lower. And so and in general, on average, the upper ocean was fresher. And the gradients below the mixed layer were also a lot sharper. And so, so what we see is that the ocean was more stratified during the ice expansion period, and that possibly could have been suppressing the ventilation of warm water. What drive this increase in surface pressure is still unclear. I haven't done like a proper freshwater budget, but there are multiple candidates. We could have a change in precipitation. We could also have a change in sea ice advection across the Weddell Gyre, and also a change in upwelling rate, which is impacts on salinity in the mixed layer. And so that's still TBD. Okay, so so we've observed these changes in using the in situ data, and we, so the next thing I want to do is sort of try to first build some intuition for, how upwelling and freshwater fluxes should impact sea ice in this region, and then try to quantify or constrain the role of upwelling on these sea ice anomalies. And the way we're going to do that is using a very simple toy model. Our starting point is sort of your standard energy balance model. I'm showing here, this is sort of, I took this model from Till's 2015 paper and sort of reduced it just to, just one dimension, one spatial dimension horizontally. And typically what's done with these models is that you just impose this constant ocean heat flux of the ice. And what we're going to do is something a little bit more, slightly more complex. And so we're actually going to evolve and solve for this ocean heat flux. And we're going to do that in using relatively simple 1D ocean physics. And so we're going to initialize with this temperature salinity profile. And so in the background, we're evolving this advection diffusion equation in the vertical. And then in the mixed layer, we're essentially using the Price-Breller-Pinkel mixed layer physics to evolve the mixed layer depth in response to wind-driven mixing and also surface buoyancy fluxes. This is obviously a toy model, right? And I can say a lot about what's missing. So no atmospheric feedbacks, obviously, no snow and sea ice, and we're assuming that momentum flux goes right through the sea ice, right? And so a lot missing here, but the goal was to sort of build what I think was sort of the simplest, most parsimonious model to sort of explain the physics we think is happening in the Weddell Sea. Okay, so just to sort of show you how that works, for a simple sort of run with very minimal tune-in, actually, you can get an upper ocean variability that looks kind of similar to observations. The white here is showing the mixed layer depth. Over the right here is showing sea ice thickness. These are slightly off from what we think, this sea ice thickness is a little bit too thick. And with some tuning, you can make it match observations, but that's really not the goal here. The goal is to sort of build some intuition. And so for this run, we basically set everything constant in time except the incoming solar radiation. So that's the only thing that's driving seasonality. And we have this constant upwelling rate of 3 meters per month. And so the first thing we're going to do is just see how this model responds to like an increase in upwelling. And we're going to do that really simply. So we're just going to apply this step change in upwelling rate. This is roughly 1 standard deviation computed from wind stress curl, and look at the ocean and sea ice response. And so what you get is this. And so on the top plot here showing the temperature, and the bottom plot is showing the salinity, and the white here showing the mixed layer depth. And over here, we're looking at sea ice thickness, and this is the change in sea ice thickness. And down here is the change in, or the ice season length relative to the control. And so I'm going to do is just show the anomalies relative to the control. And so what you can see is that during this upwelling period, you get a warming in the upper ocean, and more importantly, increase in salinity. And this increase in salinity is what is really critical. And because as you upwell high salinity water, it accumulates in the mixed layer, it reduces stratification. And then what happens is that you can ventilate more easily, and so your mixed layer deepens. And so this big ventilation is due to the reduction in salinity that enhances entrainment. And the result is this declining sea ice extent, declining sea ice thickness, and also the shortens the sea ice season. And then afterwards, there's this rebound that happens because now you have a cold ocean, and so the sea ice can grow more rapidly. Okay, so we can do the same sort of thought experiment with freshwater fluxes. And here I'm applying a one standard deviation increase in freshwater fluxes. One standard deviation is based on sort of ERA 5 precip. And we see something slightly different. So first you see this freshening, which you would expect from increasing freshwater fluxes. You also see this accumulation of heat at depth and this apparent shoaling in the mixed, well, the shoaling in the mixed layer, right? And so the mixed layer is not deepening as far, and so you're not entering as much heat. And then, and as a result, so during, you have a slight increase in sea ice thickness, slight increase in the sea ice season length. But interestingly, once you turn off the perturbation, there's this sort of reversal of these anomalies, because basically when you have the freshening, you're accumulating heat at depth, and so basically when you remove that freshening, there's like this delayed ventilation that then leads to relatively high sea ice loss. And so now you can probably see where I'm going with this, right? And so like you can imagine, right, you have this upwelling and this freshening that's sort of working in concert with each other to produce expansion and then potentially this amplified sea ice loss at the end of that perturbation. And just for the completeness, you can combine these two fluxes, and when you do that, what you find is that basically the stratification wins in this context, right? And so with increased stratification, with increased freshwater fluxes, you pretty much negate the reduction in stratification you would expect from upwelling. And what you end up getting is the signal that looks a lot like the freshwater only run. All right, and so the last thing we're going to do here is run an experiment where basically we have everything as before, but what we're going to do is replace the upwelling with this time series of upwelling from observations, right? And then see what the sea ice response is, right? And what you get when you do that is shown here. And so this is just showing the ice season length from 1985 to present. And what you see is the sea ice season shortens in this simple model, and the model actually predicts a minimum in sea ice season length in 2016, which is when we had this big dip, right? And so you can interpret this as what ocean upwelling would do in the absence of anything else, assuming this model is like a good representation of that. And so what you see here is that you don't capture this increase in this record maximum, and you also see this recovery and no subsequent decline after that, right? Okay, so to pull all this together, this is my working hypothesis. Still sort of kicking the tires on this set of ideas. So first, during the 2005 to 2015 period, when you had this gyre, the sea ice expansion, the gyre was in a relatively weak state, and so you have positive wind stretch-curl anomalies, which imply a weaker gyre and sort of depressed isopycnals and depressed thermocline, and that potentially, so that definitely reduced upwelling of heat, but also potentially increased the freshwater convergence within the gyre. Right? Because the gyre is divergent in the surface, and so if you weaken the gyre, you may anticipate a convergence of freshwater, but that's a speculation. But critically, you're accumulating heat at depth with increased stratification. And then from 2015 to 2016, we had this strong spin up of the gyre in response to this Windsor-Squirrel anomaly that led to enhanced upwelling, reduced ratification, rapid heat ventilation, rapid sea ice decline. And then after that, there was sort of this regression to the mean, and the sea ice recovered, and we do see that. And then in more recent years, something else is going on, basically. And it's possible that enhanced upwelling had something to do with it, but there has to be some other driver. Okay, so takeaways. So in situ under ice argofloats show that there was indeed enhanced upwelling of warm water in the sea ice region, and that almost certainly contributed to the sea ice decline that we have observed, in particular in 2016, which was in agreement with previous studies. The upwelling signal was mostly confined to the Weddell, and so this was not a circumpolar phenomenon, and so whatever's happening in the Ross Sea is mainly due to some other mechanisms, we think. And then in pre-2016, the sea ice expansion in the Weddell may have been facilitated by enhanced surface freshening. That's a speculation. We haven't done the actual freshwater budget, but it's really hard to explain why there's like sea ice at record maximum without enhanced ratification. And lastly, the more recent last 5 years sort of seem to be quite distinct from like the previous sea ice loss, and so I think something else is going there. And again, no conclusive ideas there, but one potential is that there's increased storminess because of the polar contraction of the circumpolar westerlies. And we have someone working on that in our group. So looking ahead, we'll see ice recovering in the Antarctic. I'm not going to make any prediction because I'm probably going to be wrong, but if this SAM trend holds and you have this persistent upwelling, then that would favor reduced sea ice extent because of enhanced upwelling. But the wild card here is going to be the freshwater fluxes, and with the contraction of the circumpolar westerlies, we expect more storms, potentially more precipitation, and how those two will compete will determine sea ice trends in the future, and so that's to be determined. Okay, I'll stop here. Oh, one more thing. Yes. I think we also need to rethink the two-type field hypothesis, right? And so I talked through that earlier, and I don't think this idea is wrong, it's just incomplete. And it doesn't factor in freshwater fluxes, first of all. It also doesn't help us with internal changes. And so I don't think it's out of the question to sort of, think about this in a sort of simple theoretical way and come to some scaling arguments for like how the sea ice should respond to changes in both circumpolar westerlies, winds over the gyres, and freshwater fluxes. So with that, thank you. Now I'll take any questions.
Hey. Really nice talk, thanks. So I'm just wondering about the seasonality of the SAM signal, because as far as I know, the SAM trend is mostly a summer signal, right? Mm-hmm. Or annual mean, but in the winter there's been actually different changes. So more, the wavy component is getting more influence, more permanent. So what did you find about the seasonality of this, apart from the annual mean?
So your question is about the impact of seasonality of SAM on sea ice. So I haven't explored that explicitly, and so you can imagine with this toy model, you can look at like what if upwelling happened primarily in the summer versus winter, and what the impact might be. I actually haven't done that, but from what we see, at least in the observational record, so like that 2015 and 2016 upwelling anomaly, that was throughout the whole year, right? And so, yeah, it's a good question. And then I think for all these fluxes, these perturbations, freshwater fluxes, upwelling foresee potentially storms, the seasonality of when those perturbations are applied are really important, but we haven't looked into that explicitly.
All right, we have a question online from Gavin, if you want to unmute yourself.
If I brought them in at the end of August and asked to get a booster.
Hi there.
For the RSV.
Thank you very much for the talk. You mentioned the role of freshwater forcing, which I think is interesting, but you didn't mention what I think is likely to be the biggest variation in freshwater forcing, which is the meltwater coming from the ice shelves calving and from the grounded ice itself. We've seen big increases in that flux over the last 20, 30 years, and very recently we saw a reverse of that flux, right? So there were mass gains on the grounded ice portion, and as things kind of grow back on the ice shelves, there's a lot of variability there as well. There's a bit of an advert for the talk that I'm giving on Thursday, which I haven't quite finished yet. But do you think that that plays a role? Is there an interplay perhaps between the expansion of the sea ice, the snowfall falling on the shelves and the grounded ice, changing the freshwater balance and then affecting the sea ice again?
Thanks for the question. Short answer is absolutely, and it's sort of inadvertent omission on my part to not mention glacial meltwater fluxes. I do think, though, there's a question of timescale, and I think for sort of the interannual timescales, fluxes, precip, snowfall, and sea ice advection will probably matter more, but certainly looking, decadal timescales going forward, the meltwater fluxes are, in my opinion, a huge emission from climate model projections of how the sea ice will respond around Antarctica. So point taken, I think meltwater fluxes will be critical, especially in the long-term trends.
Thank you.
Lily?
Hi, Earle. Thanks for a great talk. This is Lily Dove. I am curious about your thoughts. I hope you can help me reconcile something. So by shoaling, we know that the circumpolar deep water layer, or modified circumpolar deep layer, is shoaling, which inherently means that the winter water layer is thinning, right? Mm-hmm. But we know that this is a time period of sea ice expansion, meaning that there's a lot of sea ice growth. Mm-hmm. Which is what drives winter water formation. Mm-hmm. So I would expect, maybe naively, that with enhanced sea ice growth, you would have deepening of your winter water layer. Can you help me reconcile that thought?
Yeah, and so I think you maybe also be referring to a sort of a preprint that's out about the role of winter water layer thick, variability. Yeah. So for the ice expansion period, yes. So you're right. If upwelling was the main thing that's going on, you would expect mixed air deepening, and you would expect the thinning of the winter water layer. But the fact that you're not seeing that, I think, is further evidence that there was enhanced surface freshening, which was, preventing the, sort of offsetting the destratification effect of upwelling and preventing the mixed air depth from deepening. I didn't show a time series of mixed air depth, but you actually did see shoaling of the maximum wintertime mixed air depth during the ice expansion period, which is, I think, further evidence that there was some freshening counteracting that.
Maybe it's snow.
Maybe it's snow.
All right. Great talk. So you mentioned that the Ekman upwelling, which leads to less stratified water, leading to loss of sea ice. Mm-hmm. I like that. And then you said it's likely related to sun, right? At least to 2015.
Yes.
And do you go back in time? How special is this SUM event?
I'm not going to search for the slides. So it wasn't that, it was anomalous, but not record breaking in of itself.
So that means that this kind of event should have happened like in the 80s and 70s, 60s. If you go back in time, then something similar level have happened in the past.
Well, there is that long-term increase, and so the magnitude of SAM has become more positive over time. But I guess if you do relative to like some background trend, that deviation wasn't that anomalous.
Thank you.
Yeah.
Thanks for the great talk, Earle. So you stepped through this set of experiments where you did like a pulse of wind and then a pulse of freshwater and then the realistic wind, and I was kind of expecting the realistic time series of freshwater forcing. So could you talk about why you didn't do that next, and is that just because you don't trust the products?
Yes.
And then I have a follow-up question.
I started going down that path, and I sort of realized that if you look at the precip trends in ERA5, they don't show a huge trend over that period. But I also think, so that's part of it, and also I think shifts in, so that's part of the freshwater budget. There's also sea ice advection is also a big part of it, glacial meltwater, as Gavin mentioned. And so I didn't show it because I think it's missing too many things and for it to be useful. But that's something I'm sort of thinking about how to set that up. So, yeah.
Thanks. And then the follow-up is, do you think there's a role for wind-driven horizontal convergence of freshwater related to the strength of the gyre?
Yes. And so I think that is sort of my current leading hypothesis for why there was freshwater convergence during the ice expansion period. So the gyre, as I mentioned, is it's a cyclonic divergent gyre at the surface, and so early on in like the early 2000s, the gyre was relatively weak, and so it was not exporting potentially not exporting sea ice to the open ocean as efficiently, and so that potentially could be a mechanism for why there was like convergence of freshwater during that time, but I'm not sure.
Thanks.
Thanks, Elle. That was really, really cool. And I feel like this has kind of been touched on a little bit with answers to the other questions, but just to address it a little bit more directly. So your idealistic model, when you're looking at the sea ice cover, that's thinking about sea ice growing and melting like in situ, right? Yeah. So how do we kind of like bring this together with dynamic sea ice movement? How much of the sea ice extent anomaly that you see in the gyre do you expect to have been ice that formed locally versus was transported in there by dynamic sea ice patterns and winds?
Yeah, that's a great question. And so obviously this 1D model can't sort of answer that. And sort of the implicit assumption with this experiment was that, at least for the core of the Weddell gyre, like much of what we're seeing can be explained by 1D vertical dynamics. That's a somewhat questionable assumption, but I think it's good enough. But if you care about sea ice area, then you would need a sort of a different framework. And I think also, so I didn't mention this here, but I actually started with a 2D version of this model. And it got way too complicated, so I went back down to like just 1D. But I think that would be the next step to sort of, especially in trying to reconcile like the two timescale hypothesis and stuff like that, to have like a 2D version of this model. And you have to figure out some intelligent way of affecting sea ice in that framework, which I haven't figured out yet.
Yeah, and I guess also I also kind of meant that question in terms of the ability to have a freshening. I guess your like surface freshening, like the balance of where the formation is happening versus where the melting is happening is going to be important to that stratification question.
I think to answer that question, your best bet might be to actually use an actual sort of GCM, right? And like SOCI has its issues, but like I would start there, or similar data simulated models that I'd make that jump, instead of trying to like
cool, thank you.
reinvent ice advection.
That was an excellent talk, Earle. Thanks so much. I'm going to ask again a similar question, which is thinking more about the moving away from the one-dimensional structure, but rather than the surface, what about the role of the gyre dynamics for actually the heat accumulation that's not just due to the changes in stratification? Do you think how the heat is coming into the gyre via boundary currents or otherwise was also impacted by the wind stress curl or SAM anomalies?
Oh, absolutely. So I won't go back to the slides, but so I did show like a figure showing the distribution of T max, and you can see this sort of, in the southern limb of the bidial gyre, this tongue of warm water coming in, right? And so I would expect that with a stronger gyre, you'd have more inflow of warm deep water or circumpolar deep water from the circumpolar channel, and like that warm water at depth would circulate further along the gyre. And so there is a question about the horizontal supply of that warm water, and then also the sort of vertical availability of that water to impact sea ice. And I mainly talked about like just the vertical component, but the delivery of that water into the gyre is also really important.
And I'll just mention it because I think it touches on a few of the questions we've had earlier in the program. Is that I think this is a nice mechanism now that starts to couple the sea ice, the gyre dynamics, but ultimately, as you said, it's coming in through the boundary, and now you start thinking about how it interacts with the shell and various things. So that's really, really nice.
Thanks.
Oh, we have more questions. Yeah, go for it.
Yeah, thanks for the great talk. I was curious about, on the observational side, which you started with, I was wondering about what the prospect for Argo coverage is going into the future, and also if you'd considered using MEOP data to supplement, especially maybe near the Ross.
Right. So future of Argo is, I'll be optimistic and hope that the current state is maintained, and there's definitely efforts to expand the number of floats in the sea ice regions. In terms of MEOP, I did use it, and but I excluded it from the analysis for a couple of reasons. One was that it was just a lot of noise in terms of tracking Tmax, and I think part of that is just how the seal data is saved. Like they sort of sparsify the vertical profile and sort of extract the essential shape, and I think, but that leads to small errors that I think are actually important for how we're tracking Tmax. But it could also, I think it is useful. I just haven't figured out a way to incorporate it in the analysis effectively. The other reason I excluded it here is because for sort of the part of the bidial gyre I was looking at, which was deep within the ice pack, the seals really don't go there in the winter. They tend to hang out on the periphery of the ice, the sea ice, and near the margins or not near the ice edge. And so there wasn't that much overlap of Argo and seal data in the bidial gyre, but yeah.
Okay, we still have plenty of time for questions, so don't be shy. Okay, Patrick.
Patrick Taylor, NASA. This might be naive, but I'm trying to put together ideas like from Lily's talk yesterday and from the talk this morning, Chang's talk this morning. So, this expansion and contraction of the sea ice, is there a role for the eddies in this region for influencing what's going on here?
Yes. That's my answer.
You got anything else that you could inform a non-oceanographer?
Yeah. I won't try to answer there's so many ways, right? And I'll highlight one potential area where I think it's critical. So in thinking about going back to the 2 time scale hypothesis, and so the sort of idea of you increase the westerly winds, you spin up the upper cell. That response is going to be dependent on how the eddies respond. And so you have this wind-driven overturning that's being sort of partially negated by this opposing eddy overturning. And so one of the sort of challenges with looking at some climate models is that they're not eddy resolving, and so their eddies are parametrized, and so there's a question of is the eddy response appropriate? And I mentioned Ed Dodge's paper here, and he found that when you actually resolve the eddies, you tend to have little to no long-term warming in response to increased westerly winds. And so that's one area where I think eddies are critical. I'm sure there are many other ways, but that's just one example.
Great talk, Earl. So your simple model has 2 timescales, right? Because the sea ice should have a sort of timescale of a few years, and then the mixed layer should have a timescale of order a decade or so. And I'm wondering whether you can explain the sort of diversity of model responses with your model.
That's an excellent question. I would expect, I haven't actually thought about how many timescales are in this model. I think there's more than 2. Because you have the upwelling timescale and the diffusive timescale, the mixed layer heat capacity timescale. But sort of one of the ideas I didn't sort of go over here is that I think, I showed the spaghetti plot of like the response and, to sea ice to westerly winds, and some might say that's evidence that the models are not good. I think it's probably I think it's actually reflective of like the internal variability of the actual system to a large extent. And so one of the things I want to do, maybe not with this exact version of the model, but something a little bit different, is to sort of see like, do a parameter sweep of different force in different initial states and see sort of what type of responses you can get. And I think one could probably recreate a spaghetti plot like that with like, very minimal changes in the initial state of the ocean or the force in. But I need to think a little bit more about how many timescales are actually there.
I think this also gets at like some of the other questions about freshwater forcing from ice shelves, right? And as you said, that adds a new, longer timescale to the problem. But if there's basically this overarching long-term trend, that might be engaging sort of different timescales of the system, you could consider like forcing your model with integrated basal melt rates from observations over the last few decades, which we have, and seeing whether that might do a better job of explaining some of that variability.
Yeah, absolutely.
Yeah. Really nice. Thanks.
Just keep it going.
Earl, you mentioned in response to one of the earlier questions using more comprehensive models to test some of these things, and you mentioned SOSI, which integrates observation, so presumably it's closer to reality. Did you exclude like free-running climate models because they're not even reproducing some of these like basic mean states that they can do this? And I'm thinking in particular that a lot of pre-industrial global climate model runs have these like super polynyas that are very far off from these kinds of interannual variability dynamics that you're showing.
Now, there's absolutely a role for comprehensive climate models, and one can think of like recreating these experiments like more realistically. I think my one point there is so a lot of studies have sort of focused on sort of the impact of SAM. And I think SAM is like such a multifaceted phenomena. It involves winds, it involves freshwater fluxes, that there's sort of, different spatial structure to the anomalies. And so I'd probably go in the direction of like being a little bit more process-based and say changing like the winch curl of the gyres specifically and stuff like that. But yeah, to answer your question, I think there's a lot one could do with like comprehensive climate models, and I think they get a bad rap, but I think they're better than people make them out to be. It's just that the system's really hard to simulate, and there's a wide range of potential possibilities, and we just happen to be in one realization, and so yeah.
Okay, hi Earl, sorry. Good talk. I'm wondering, when you were doing the 2D setup, like what were like the most important processes that you wanted to include that like were making it complicated?
It's a good question. So I didn't get very far, and the challenging thing was sort of trying to recreate like ocean overturning in a realistic way, and so it's relatively easy just to like have a stack of 1D profiles and maybe have some horizontal diffusion, but that's not good. And I think you want to sort of do something. I think one of my ideas was to sort of try to incorporate like some of and these ideas using like sort of a isospinal layer model and sort of, resolve like the isospinal structure that way. But I didn't get very far with that, but that's a challenge yeah.
All right, I think Earle has had enough questions for today. And you passed your PhD defense, so that's good. So we don't have lunch until 12:15. You feel free to check out the posters, as I mentioned in the morning, get some air outside. Otherwise, thank you very much to all our 3 speakers. They were really great talks, and we reconvene at 2 p.m.